Let me know when you are done. Okay. My screen just went black, didn't it? Yeah, let me fix that. Yeah. All right, all right. So I'm just gonna damn it.
It went black again.
Yes, yes, I know. Just give me a second. Yep, should be good now. Yeah. So the thing I'm gonna talk about, as someone asked in a bit, you could have just waited for 5 minutes and found out, but so yeah. The thing I'm gonna talk about is the Hadwiger-Nelson problem, which is something I did talk about briefly in my Moser Math Camp lectures, if any of you attended that. So there will be some slight overlap of the material at the start of the thing, and but just to be patient, new stuff comes soon enough. Yeah. Anyway, so what is the Hadwiger-Nelson problem? It can be like, it has a very natural, simple to state statement. So what we're looking at is something called the chromatic. There's some echo apparently. I can fix that.
No, there's
Yes.
not.
Is it still there? To whoever said there is an echo. Awesome, awesome. Yes. Hadwiger-Nelson problem asks what is the chromatic number of the Euclidean plane? So what is the chromatic number of the Euclidean plane? Effectively, we want to color the plane, color the Euclidean plane with say some number of colors. The problem asks what's the minimum number of colors you need so that no two same colored points are at a distance of one from each other. So we'll denote this minimum number as chi. So this is an open problem, by the way, which is why we won't be solving in this class. If I could solve it, I would be doing a class at this camp. This is very wide open, but there have been some partial progress, and the partial progress is worth looking at. So what we know for sure is chi is definitely greater than or equal to 5, and it's definitely less than or equal to 7. So, and it's definitely an integer. So these are the possible options. So let's see how humanity as a whole narrowed down the values of chi to this relatively small set. So first of all, let's try proving chi greater than 3. So put in simple terms, this means that you have to prove you need at least if you use only two colors, you cannot color the plane so that no two unit distance points are of the same color. Can anyone tell me a brief sketch of how to do this?
Equilateral triangle.
Yes, of course. People who have seen this from my MMC lectures may wanna refrain from spoiling stuff from others, but I don't really care. It's up to you. Yeah, so equilateral triangle is the correct answer, even though it's not really a proof, it's a phrase. So to expand on that, draw an equilateral triangle and make sure the points are points, not circles. So suppose you have only two colors to tile these things, so to color the plane. That means by Pigeon principle, some two of these color points will be the same color, but there by construction a distance 1 from each other. So this is true. This is the first non-trivial problem that we'll encounter in this problem, and a non-trivial case. So, and this teaches some fairly useful lessons. So people who haven't seen this before, try to come up with a proof, I guess. If not, people who have seen this, I'll ask you guys. So yes. So the basic idea behind the proof is.
Point the distance
Sorry, say that again.
So point the distance of exactly one should have different colors. Is that right?
Yes, yes. I should probably write down the problem statement somewhere for what's the minimum number of colors necessary to color the plane so that Euclidean plane is not z square, it's r square. So that no points at a distance of 1 as the same color. If you want, you can also try proving this for z square. I guess that's not a particularly hard problem, but it's a nice exercise. What do you think? What do you guys think the answer is for z square? If you're trying to just color the integer lattice with colors, so that no 2 points with unit distance are the same color, how many colors would you need?
I didn't get the question.
Yes, so someone in the chat asked if Euclidean plane means z square, the integer lattice.
I think two colors, right?
Yes, 2 colors is correct, but someone didn't get the question, so let me get back to you. So someone asked if Euclidean plane is just z square, which is just xy for x in z and y in z, and it's not. Euclidean plane is actually r square, but that's what I mean by Euclidean plane. But that's an interesting variant to think about. How many colors you would need to color z square so that no 2 points at unit distance are the same color. Yes, someone was saying it is 2. Can you explain?
Like if x plus y is even, put one color, x plus y odd another.
Absolutely.
Yeah, I mean like it's just 4 colors.
Exactly. Only 3 colors. We cannot color the plane such that no 2 distance or monochromatic pair occurs in the entire plane. So any ideas on that so far? So here are some things you need to care about. So what's the reason this construction worked? The only reason this construction worked was we have information about this configuration of 2 points at a distance 1 from each other, and we know they have to be of different colors. So the only configuration we have information about is this, and we want to construct an example that has multiple examples, multiple interrelated examples of this construction. So even in this picture, we have 3 examples of this construction, and they are sort of connected to each other, which is why this condition actually gives us anything non-trivial. So what you want to do is construct something that has multiple examples of 2 points being at unit distance. So yeah, ideas.
Regular hexagon with center.
Let's give that a try. That's a very interesting configuration. Unfortunately, it doesn't quite work. You can color that with 3 colors. Let's just make this yellow and put red and blue alternately here. So this doesn't work, but this is an interesting configuration for later purposes. We will revisit this configuration later. So other ideas.
We can prove using this configuration that any 2 points which are root 3 apart have the same color, and we can just consider a root 3 one triangle.
That is correct. That is the standard way the proof goes. Yes. So yeah, anyone care to explain why 2 points at the root 3 must be the same color?
Construct equilateral triangles like this, like the RYR and BYR on the right
Correct.
side.
Absolutely. So if we construct 2 equilateral triangles joined side to side like this, That means, suppose this is red or something. So if we have only three colors, these two have to be two different colors from this. So for this, we have only the first color left. So these have to be blue, yellow, or yellow, blue in some order. So this has to be R. So what this proves is, since we can draw this diagram for any 2 points at a distance of root 3, that means any 2 points at a distance of root 3 have the same color. How does that prove? How does that give a contradiction?
Triangle with sides root 3, root 3, 1.
Correct. Yeah, I'm gonna make you guys work a little bit if that's. I mean, I don't care if that's not okay with you. Anyway, so yeah, this is a contradiction. So let's this proof was basically on two steps. First, you prove a lemma, which is points at a distance of root 3 have the same color, and then you use that to construct a fairly simple diagram. So, but this was just one singular construction that worked. So let's see if we can phrase this argument into just one singular diagram. So how did we prove with this again? Give me a second. Yes, we have enough pages now, so we don't need to worry about space. Yes. So how did we prove that root 3 is gives same color again? So we took this configuration. So in this diagram, this and this, these are the points that are supposed to be of the same color. And in the final configuration, we had this root 3, 1 triangle. And so effectively, the argument looks something like, you take this is a terrible diagram. Let's see, yes. You take this root 3, 1 triangle, you erect this diamond shape on one side and a second diamond shape on the other side. And then you can effectively check that this particular diagram cannot be colored by 3 colors. So yeah, let me draw a cleaner version of this. Don't know if something one is trying to, yeah, one's trying to enter. Yes. So this particular diagram is what proves that chi is at least 4, right? And there's a very nice name for it. This is called the Moser spindle. So yeah, so yeah, what did we learn from this? Point 1. Equilateral triangles are good. So for proving things about points at unit distances, equilateral triangles are super good. The second thing that we learned from this is it's a good sign if you can prove 2 points at a distance d must be of the same color. At any stage in the proof, if we can prove a statement like that, that's a good sign, because we can construct more stuff out of that. And construct how exactly? Given 2, you can take rotated copies and merge them. What does that mean? So in this diamond configuration, we have this point 2 already done understood. We have 2 points at a distance root 3, generic points that they have to be the same color. if we manage to prove something like that, it's usually a good idea to take another rotated copy of that, so that this is the apex and the two opposite vertices are at a distance of 1, and sort of merge the diagrams together to form this spindle-like thing. So these are 3 heuristics that will be later useful. So keep those in mind. So when we are looking for proofs along these lines, someone suggested this hexagon. Yes, I take an oil long to draw. This does not give a counterexample, but here's a puzzle for you. You can actually add 3 points to this at some strategically placed parts, so that this does give a counterexample to chi equals 3. To disprove chi equal to 3. Just prove chi is greater than or equal to 4, I guess. So what you want is add 3 points in this diagram so that the resulting diagram cannot be colored with 3 colors. I'll let you think about this for a few minutes. Where would you add those points? Yes, that does actually end up working. So suppose we did, perfect, yes. So we take this copy of the equilateral triangle with side length 1 and put this inside the hexagon, says that, say this distance we make 1, that we can obviously ensure that. I'll leave this as an exercise to show that this doesn't actually have a coloring. So yeah, we have proved in chi is at least 4 in multiple ways, in fact. So the next big step that would be proving chi is at least 5, and that's where humanity's knowledge of this problem is currently at right now. So this was proved very recently using a huge ass graph. So I mean, out of consideration for your sanity, I won't ask you to come up with that. So what we're going to do is look at a brief look at how exactly the construction goes, and sort of try to understand the general heuristics that comes into play. So yes, the goal is to construct a huge graph that cannot be colored with exactly 4 colors. So we do that in several steps. Yes. Remember this configuration? This one. Told you guys this one is going to be important. So epic foreshadowing. This is going to be very important. We will call that an H. Ways to sort of color this up. We'll look at some good monochromatic triplet. Some have a monochromatic triplet, others will not. The second step would be to construct a huge graph L with copies of H inside, such that any four coloring forces at least one H to have a monochromatic triple. Does that sentence make sense? At any point, if something does not make sense, feel free to
Can you please repeat the point one?
Yes. So basically, what we do in this step is we construct a huge as graph that has several copies of H inside it. In fact, exactly 52 copies, and says that the L will have the property that given any good coloring of L with four colors, forces at least one of the copies of H to have a monochromatic triple in it. Remember, there are two ways to color the hexagon H, one with one that involves monochromatic triples and one that does not. So we will construct L says that no matter how you color L with four colors, at least one of the H's will have a monochromatic triple in it.
Does H also consist of center of the hexagon?
Yes, the H has 7 vertices. Yes.
Okay.
And that is our second step. Our third step will be,
Can you please repeat the definition of monochromatic triple?
sorry,
Definition of monochromatic triple.
just 3 points of same color.
Okay.
So was there something else in the chat? Yeah, cool. So monochromatic triple is just exactly what it sounds like. It's a 3 point with the same color. And the third step will be we construct a graph, huge graph M, that has a copy of H inside it, and so that no coloring of F contain no so that no four coloring of M has involves giving the H monochromatic triple. Yes,
What is the difference between M and L?
they are two different graphs. Okay, so L is such that whenever you four color L, at least one H will have a monochromatic triple, and M is a different graph. So L has multiple copies of H inside it, 52 in fact. M will have one copy of H inside it, such that no matter how you four color M, you have to give the H a monochromatic triple. So does the difference make sense? I mean, they serve different purposes, sort of.
What is? Can you repeat the purpose of M?
M. So M will have a single copy of H inside it, and we will set things up such that no matter how you color M with four colors, so that adjacent vertices are not of the same color, you cannot avoid giving this copy a monochromatic triple.
Oh, so
Oops, didn't see that. Yeah, I think I cleared the queue.
by monochromatic triple, do you mean that there will be three vertices such that all are pairwise distance one apart?
Not necessarily. There will be just three vertices inside this copy of H. Which are of the same color. That
Okay.
still doesn't prove anything, but I'm getting to the finish. So now that we will have L and M, we can sort of combine them in a very horrendous way to get a proof. How exactly? What we will do is we will take 52 copies of M. and combine them so that their HS, every M has a copy of H inside it, right? So we have 52 copies of M, and each of them has a copy of H inside it. So we will arrange them so that their internal HS, their, that's a weird way to say that, their internal H hexagons, they form an L graph. Ruminate over this sentence for a bit. We have L that has 52 copies of H inside it, which has certain properties. We have M that has exactly one copy of H inside it that has certain properties. We are taking 52 copies of M, combine them so that their internal copies of H, they match up to form an L. This gives a contradiction. Do you see why? Refer to the definitions of L and M.
Yeah.
Okay, when I said do you see why, that was meant to say why.
Oh no, I don't see.
Okay, yes.
Because like by definition, there's 52 copies of M, it
Mhm.
forms L, which is supposed to have at least one monochromatic hexagon.
Exactly.
But by definition, M does not have any monochromatic hexagon.
Yes, correct. Any hexagon with a monochromatic triple in it. Yes, that is exactly correct. Now, this part is easy. Step 1, where we look at the colorings of the hexagon. That is relatively easy.
I have
Yes.
one doubt.
Go on.
Doesn't M imply that the H has a monochromatic triple? That any four coloring of M gives a monochromatic triple.
That is correct.
And then like L also should have one monochromatic triple. So like, what's the problem when you combine them?
Hold up. I may have.
So is the proof complete?
No, hold up. Something went wrong here. No. Sorry. M does not have a monochromatic triple. So read the statement again. No four coloring of L involves getting the H a monochromatic triple. So no matter how you color M, you should not be able to get a monochromatic triple wala hexagon. Yes, sorry, I was briefly confused there. Yes. Yeah, so this is all correct. So if it's still not making sense, just let me know. Yeah.
It's fine.
Okay, cool. So there are 3 steps, that's what I said. The first step is easily doable by hand. There's just case checking, and I won't make you guys sit through that. The second step is basically spamming in its purest form. That will mostly be by hand. The third step, I'll tell you guys how to construct M. But the fact that no four coloring of L involves it's getting a monochromatic triple, we won't be able to prove that because that involves computer checking. Like the official proof is checking by computer. It's not pure brute force. You can make some reductions, but it's still not a very enlightening proof. So you'll have to believe me on this part. So let's jump into it. Now this is our thing. Yeah. So if you just sort of sit down and look at all possible colorings of the H, you will end up with some list sort of this. So basically, you're looking at colorings up to rotation, reflection, and recoloring. The 3 R's of education. Yes. So
What is the last one?
recoloring. Basically, you switch the colors, right? You switch black and blue with yellow and vice versa, something like that. So if you check out all the, well, yeah, this is something you can verify on your own. Yes, hold up. Yes, this is something you can verify on your own. So you give, without loss of generally the center, the color yellow, and then you sort of see that the outer vertices cannot have yellow in it. So there are only 3 colors and only a few possibilities. Some of them end up being equivalent. So yeah, notice that this and this have monochromatic triples. This and this have no triples. So if someone is still confused about the definition of a monochromatic triple, they should clear that up. Yes.
So it is not necessary that the three triples form an equilateral triangle.
I mean, in this case, it would be, but that is not none of our business. I mean, we won't use. I mean, in these cases, you can see that they do form an equilateral triangle, but point one, they are not well of just side length one, and point two, that won't actually be relevant at all.
Okay.
Cool. So the next thing we'll construct is this graph called J, which consists of 13 copies of H, and it looks fairly normal. This is our J. And yes, I have labeled two vertices here, A and B. You will see why in a bit. So what we are going to do is, let's look at all possible 4 colorings of H in which no copy of H contains, we will look at all 4 colorings of J, so that no copy of H has a monochromatic triple. Remember again what we're trying to do here. We are trying to construct M such that any 4 coloring forces a monochromatic triple in one of the H copies. So to get a contradiction, we should look at 4 colorings that do not have a monochromatic triple containing hexagon, right? So that's what we're doing here. So the next step is to look at 4 colorings of this graph such that no copy of H contains a monochromatic triple. And again, I won't make you sit through the case here because it's not particularly enlightening or anything. But it's not particularly hard either. I recommend you verify what I'm about to say later in your own time if you want to. So basically, the sort of logic you use is there are only 2 possible colorings of H that does not contain a what's it called, a monochromatic triple. And so you basically start from the center and you, without loss of generality, call it Y, and then this hexagon, this inside all the hexagon can only be of 2 possible configurations. Then you sort of build up on that, and if you carry out the case checking, you will end up with 6 different possible colorings of J. Here some vertices are black because basically by black I mean they can be of any color as long as they are not directly contradicting to each other. So basically, for example, here's yellow and red here, and this black would be green or blue, and the other one would be the other remaining color, and it doesn't really matter which one you choose. So yeah, think of the blacks as blank spots. So up to rotation and reflection and recoloring, there are only 6 possible colorings of J. So we could sit here and derive all this, but instead of that, let's look at what we can see from these. Yes.
Why does the third coloring have a monochromatic triangle?
Why does it have a monochromatic triangle in any of the H copies? Does it?
Okay, so like except for the third, which I guess we have to look for more, others have a monochromatic triangle.
Okay, the goal was to make sure nothing has a monochromatic triangle. Can you hold up?
I don't see any monochromatic.
I don't see any monochromatic triple either, so I don't know what you're talking about.
No, we wanted to have a contradiction, right?
Yes. So we are looking at colorings that do not have a monochromatic triangle in one of the hexagons. So see, if we assume that none of the internal, yes. So this has copies of H inside it, right? Multiple copies. This is one copy. This is one copy. And we're looking at
Okay,
colorings in which
okay.
none of these copies have a
But I thought
monochromatic
you were
triple.
defining that Okay, okay. Acha, I thought you were defined that it could be of any length, like not
No,
even.
not that way.
Okay,
So
fine.
we want the internal hexagons to be triple free. Yes. So if you stare at these diagrams hard enough, you'll notice something. Remember how we labeled two vertices separately, A and B? Two vertices in this position will be called linking vertices. What exactly happens in the linking vertices in our case then? If we look at the colors of the linking vertices, you will notice that the linking vertices of in diametrically opposite positions are always of the same. Well, not really, but like linking vertices, if you look at them, they only have two colors. So in this case, these are the linking vertices, right? So they all have the colors yellow, which is the same as the color at the center. If you look at this case, all of these have only two colors, red and yellow. So because we are looking up to, so basically that means if you look at the linking vertices, they can only have the either the same color as center and they can only occur in very specific positions. So they can either be, in this case, a complete hexagon of the same color, or they could be, for example, in this case, 4 consecutive yellow vertices and 2 consecutive vertices of the second color. In this case, this configuration can also happen. And these are pretty much the only possible configuration. In this case, we just have a copy of the above configuration. In this case, we just have a copy of this above configuration here. Yes. So remember, one of our heuristics was this. Whenever you see that certain vertices are forced to have certain colors of certain limited set of colors, then you can sort of take copies of that configuration and rotate that so the constrained vertices are at an unit distance from each other. That's what we did with the Moser spindle. We figured out that these two vertices have to have the same color, so we took a rotated copy of that, and so that these two vertices are at a unit length. We're going to do the same thing with J, except we're going to rotate by the around the center. If you do that, this is what you get.
So what have we proven?
We haven't proven anything significant
Okay,
so far.
one thing could you do?
Sorry?
Okay, so like I have one doubt here. In the second figure, if you look at the bottom right and bottom left hexagon, the black could be red, right? So there's a possibility
No,
of
the black could not be red because
monochromatic
there's already
triangle
red
there.
here. We are considering coloring that do not violate the condition that unit distance. So we'll only consider so-called proper colorings, right? This can't be red because there is already red here. Is that clear?
No, like the right, above right.
This one?
Just, yes, this one, yes.
Which one could be red? This one?
The one to the right of that and the rightmost of that hexagon could be red, right? Yeah.
Yes. So by black, yeah. I don't mean it could be anything. By black, I mean it could be anything as long as you respect the conditions, and the specific choice of it doesn't really matter for our purposes. So it won't be red because I'm not allowing red here. I'm not allowing triples. Okay. Yeah. So what have we proved so far? That is a very good question.
Okay, I didn't understand why, like.
No, so
okay, sorry. Like I didn't understand what. Like,
we're only looking at 4 colorings, is that no copy of H is a monochromatic triple. And when I show these colors vertices in black, I mean there are several possibilities for these, and I'm not bothered to show what happens there exactly. Black does not mean it could be anything.
Okay, so like we are not proving. Okay, so we are not proving that J has no copy of.
No, we are only looking at
No
colorings that
monochromatic
has
triangle.
no monochromatic triplets, right? We are not
Okay.
even considering
Okay.
colorings that have monochromatic triplets in them.
Okay. Okay. I see.
So
Gotcha.
what have we proved so far? So we have proved if J is 4 colored and has no hexagon with monochromatic triples, then you can say that the linking vertices can only come in a specific can only have uh, these specific configuration specific configuration. Under this assumption, we can say that the linking vertices have only this specific configurations. So now what we're going to do is we are going to take a rotated copy of J and rotate it slightly so that the linking vertices of the new copy are exactly at a distance of 1 from the linking vertices of the old copy. So if you can identify the copy of J here, these were our linking vertices. This is harder than it looks. Yeah. These were our linking vertices. So we have taken that J and rotated it slightly so that this vertex ends up here, this vertex ends up here, this vertex ends up here, and so on. And we have rotated so that this distance is exactly 1. So there's now an edge here, and we can't keep these to the same color. Now, yes.
Also, it seems there's someone in the waiting.
Okay. I don't see a request to join, so.
Like it was a few minutes ago, they said.
Oops. If someone comes in again, just let me know. It's sort of hard to keep track of every notification, so just let me know. Okay. Yeah. Yes. Where was I? So yeah, this is now this graph K, which has 2 copies of J and several copies of H inside. Now imagine 4 coloring this so that no H has a monochromatic triple. So what happens then? Note that these six linking vertices that we just saw can have only one of the above 6 configurations. Similarly, these 6 linking vertices that we just saw can only have one of the above configurations. And one can check that no 2 above configurations are actually like hold up. Sorry. And you can actually manually check that no 2 of these are actually sort of compatible, except this and a copy of itself. Sorry, oops. Except these two. So the configurations of the two sets of linking vertices must both come from these two. Can anyone give a quick argument as to why? Anyone is still following this entire mess?
I think
Because
that
have
I
four
yellow
consecutive
vertices.
One at a time, please.
PHP on yellow vertices.
Yeah, I can't hear you at all. Say that again.
You can do PHP on yellow vertices maybe.
Yes, yes, effectively. So if one of them is this configuration, then nothing else fits because other one has to have some yellow vertices. If one of them is this one, you can again check. The other one can only be one of this, and that doesn't fit either. So the only choice is both of them have to be of this type. Yes. What does that mean? Now, what does that mean? Sorry. Oops.
I think it can't be of the sixth type too because there are also PHP on yellow vertices.
Sorry, say that again.
Oh, sorry, I misunderstood it.
Yeah. So note that the yellow for the two copies have to be both the same color, but one of the copies can have a different red than the other. So one of the configuration can be yellow and red with this one, the other one can be yellow and blue with this configuration, if that makes sense. In either case, the point is both the copies have to have this configuration. In particular, what that means is the diametrically opposite. Sorry, just give me a moment. Yes. What that means is the diametrically opposite linking vertices, they have to have the same color. So in this case, for example, A and B have the same color. So we have proved that under the assumption that no internal edge contains a monochromatic triangle, A and B have the same color. Give me a second. Yes.
But there is someone waiting to join.
Ah, okay. Done. Yes. So what have we proved through all this? If we four color this diagram, this humongous graph K says that hmm, no internal hexagon has a monochromatic triplet, then the diametrically opposite linked vertices A and B, they have to be of the same color. So what was one of our heuristics? What do we do when we have a configuration where two fixed vertices have to have the same color?
We pick that distance two things and like distance of 1 between them. Like a triangular sides DD1.
Yes, absolutely. So in other words, we rotate this is that. So we rotate this around A such that the uh, there's a copy of B somewhere here, and this triangle would give us the contradiction, because this has to be of the same color, A and B dash have to be of the same color, and they are at a unit distance, which is bad. This is what you get when you do this. We have sort of turned the figure on its side so that the symmetry is better visible. So yeah, this was our A. We took a copy of K and rotated around A by some angle such that B ends up exactly at a unit distance from itself.
But it might happen that one copy is of type 1 and the other is of type 3. In one we have 4 yellow and in other we have 2 yellow.
There was no admissible configuration with... Hold up, what do you mean? Okay, do you agree that in any coloring of this thing, this and this has to be of the same color? They may not be yellow, they might be both red, but they still have to be of the same color, right?
Which two?
A and B. This diagram is a mess. Yes, so what we saw is that two copies of G that are inside this, they have to come from these two types, right?
No, I'm not sure about that, because it might happen one comes from say 5th type and other comes from say 3rd type.
So one of the major parts of our proof was that nothing can come from the 5th type, because so what we did was to get to K, we basically took two copies of J and rotated them, right? Now, one of them you say comes from the 5th type.
And other comes from 3rd or 6th, say.
So 3rd. So there's a copy of J right above this. So there's a point here, 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 there's a point here. Since it comes from the 3rd type, two of these have to be yellow, right?
Yeah.
And two diametrically opposite things have to be yellow, in fact. But they can't be these two, they can't be these two, they can't be these two. You can effectively check the cases. This cannot happen. Does that make sense?
Yeah, now got it.
Okay, perfect. So where are we right now?
So what's the claim basically?
Yes, I'm getting to that. So we have shown that there has to arise a contradiction if we try to four-color this L. So four coloring of L so that no internal H has a monochromatic triple. Yes, we color and A and B dash are the same color, which is a contradiction. What does that mean?
So if you can prove that L cannot have any hexagon of L cannot have a monochromatic triangle, then we're done.
Correct. In other words, we have found a graph L says that no matter how you four color this, some internal copy of H will have a monochromatic triple. Right? Yes. Yes. I see. I can. Yeah. Sure. No problem. Just let me know when you come back. Yeah. So where was I? Yes. So what does this prove? We prove that no matter how you color L with four colors, such that adjacent vertices do not have the same color and stuff like that, you will always end up with some copy of H inside it that has a monochromatic triple. Does that make sense?
Why is that true?
Okay, so what we proved so far is if you try to color L with four colors, as no internal H has a monochromatic triple, then you will end up with this configuration, which is a contradiction.
Okay.
Yes, so unraveling the contradiction, taking the contrapositive of that, if you don't allow contradictions to seep in, that means at least some internal H has to have a monochromatic triple in it. Yes.
So I have
Yes.
one.
Yes, go
I have
on.
to confirm one thing regarding the configuration.
Mhm.
Can you go to the previous slide once?
Yes. This
This is yes. This is 26H, right?
this has
13.
26 copies of H. Yes.
Yeah.
No,
Okay.
wait. Does this have 26 copies of H? I forgot. Um,
13 before and 13 after rotating.
right. Yeah. Correct.
Okay.
Yes.
And that will have 52 because after
Because
again
we have
rotation.
duplicated that and sort of spread out.
Okay.
The calculation of the number of vertices won't be so
Okay, so
simple
like,
because some of them are merged. Yeah, go on.
when we're telling that there are copies of H, are we considering the minimum number of H required to build that, or the maximum number of H contained in that?
No, so we sort of built this with the copies of H inside them, right? So in this case, for example, in this J, we can clearly identify the copies of H inside. This is not a formal definition per se. We can sort of, if you want, we can sort of name the copies of H and work with that instead. So this has exactly 13 copies of H that we are looking at. Right.
Okay, so like the maximum number of H possible to
Sure, let's say that. I mean, there could be other stray copies of it. Okay, actually, there won't be other stray copies of it. So yeah, maximum possible is a good definition. Yeah. How far were we? Yes. So what we have proved is we have constructed this huge graph L so that any four coloring of L has to induce at least one monochromatic triple inside one of its edges. And if you remember, this was exactly the required second step. Read this so we can verify I'm not lying to you. So yeah, that's our second step. What was our third step? Third step was constructing M such that M has one singular copy of H inside it, such that no matter how you four color M, the H cannot have a monochromatic triple. Yes. Now, how do you go about constructing that? That's sort of a funny construction.
I didn't get what M means exactly.
Yes. So we have completed the second step. The third step is constructing a graph M that will have one copy of H inside it. See, look at this diagram. Says that no matter how you color M with four colors, the H cannot possibly have a monochromatic triple as long as you color so that no two adjacent things are of the same color.
Oh, got it.
Okay. So I'll briefly sketch how you go about constructing that with this very illuminating diagram. So can you guess what this diagram on the left is made out of? It's made out of something very familiar.
That the endpoint for
rotated hexagon.
Not quite, not rotated hexagons.
what
There
were
was
the
some.
6 points called? Uh, that 6 points in the corner. I don't remember the name. Which you said that.
Yes, it's actually made out of copies of this diamonds. So you can identify one of the copies here. Yes. So this is one of the copies, and we have sort of taken multiple copies of this sort and joined them, merged them at well, this vertex, and sort of kept rotating that to this, get this, and some 30 or something, I guess. No, 10, something like that.
Doesn't this look like a bit like in that J, which you mark the 6 point, which has yellow or red color only?
Yeah, I mean, like I think it does. I mean,
To refresh your memories, this was our J.
Oh, yes, yeah, linking vertices with the center in this.
Sort of, yes. I mean, it's effectively a circle. I mean, if you want to say it looks like J, you can't say it. Anyway, that doesn't really. Anyway, point
okay,
is,
so like, I mean, it does. I mean, it could be.
mhm. Sorry.
Yeah, so I was saying that it could be said as rotated hexagons as well, right? So like,
It
I
could
mean,
be
they are
constructed
rotated
as
hexagons.
rotated. Ah, right, yes, that's correct. You can identify this like one copy of hexagon here, for example.
Yeah, and then there'll be, I think, how many, one, two,
Yes,
three,
yes.
four,
Other will
five.
probably come in pairs of, not pairs, six triplets of regular hexagon. So yeah, sorry, that is correct too. But yeah, but the main reason why this configuration is important is it will have several copies of the nice Moser spindle configuration inside it. So what we do from here is we take V, then we construct W, which is what? All points with distance less than or equal to √3 from the center that can be obtained as that are sums of vertices of V. By sum, I mean vector sum. So what you basically do is you look at these points and you take the pairwise vector sums of each possible pair. So this and this, for example, would be give you this. This and this, for example, would give you, okay, this would give you anything.
Can you tell once how V is from, like how many copies, it has how many copies of the diamond?
I think it has 10. I mean, you can sort of count them yourself. I don't really want to do the counting. It probably has 10. Yeah. Anyway, so basically what you do is you look at these vertices and sort of take the vector sums and you pick the
I think
ones.
it is 15.
Is it? Actually, let's do the counting.
So like
Whatever, who cares?
it has 5 hexagons. Each hexagon has 3. I
So
think.
it has so but that includes some overcounting, right? So it has 5 hexagons and each has 6 vertices, so that is 30. So you're saying there are 30 vertices around the boundary, is it?
No, like I was saying, each hexagon has 3. What do you call the Moser spindle?
Yes, but that includes some overcounting, doesn't it? Hold up. Where is that?
Okay, so like here again now, I'm asking, is he asking a maximum number of Moser spindle possible contained in that, or minimum number required to build
No,
that?
no, I'm just saying how many copies of this are there, the maximum number, let's say.
And how are they rotated?
Okay,
Like are
then
they
it'll be
rotated some
30
way
then, I
that we
think.
have
Yes.
distance or at random?
Yeah. Anyway, the exact number doesn't really matter much because we are not going to calculate anything with that. So yeah. So we take V, then we take the vector sums that lie inside the distance √3 from the origin, and that gives us some huge graph W, which looks pretty bad. I don't have a picture for that. And then you take the 7 vertices. So you take 7 copies of W and put the translates on 7 vertices of the R holy hexagon that we started with, right? So this we'll call M.
Okay, so like I have a doubt. Yeah, so when we are telling that they are put on H, we're talking that we're telling that the side length is also 1 only, right?
Yeah, side length is 1. Side length is still
Side length is 1, right?
I mean this.
Okay.
Like W is a graph, not a vertex. So
Side
what do you mean by distance you take to W is 1?
Sorry, say that again.
W is a graph, not a vertex. So
Yes,
what do you mean by distance you take to W
yes.
is 1?
So W sort of looks like this flower thing, right? And that has a center in it. So we take 7 copies of W and put them so that the centers of them fall on the vertices of the hexagon. Does that make more sense?
Or I guess we
Yes.
could say that congruent points lie on the H.
Huh?
Points that are so like when we are making a copy of W, congruent points lie on H.
Yes, that's
instead of like
that's also a different way of saying that. Yes, correct. So yeah, this is what that would look like. This monstrosity is our M, and it just so happens that if you try to 4-color this by 4 colors, then this central hexagon this will have this can never have a monochromatic triple.
The central hexagon is the hexagon formed by the centers of W.
Yes, precisely. We put this on on the vertices of one central canonical hexagon, right? So that's what I'm seeing here. And this cannot have a monochromatic triple. Now, we won't prove this because the official proof is computer bashing. But if you believe me on this, that means our third step is done. And as we saw before, once we have been through these, we have basically proved that we have basically got a contradiction. So yes.
Oh, can you please repeat the definition of W once? It is not clear to me.
Someone had a question that I do not.
Oh yeah, I was asking, can you please repeat the definition of W?
So it's not pretty. Let's try to repeat that. So V is this thing. So to construct W, we basically do this. We look at pairs of vertices. We take their vector sum. So this would be a possible vector sum. This would be a possible vector sum. And we only keep the vertices that lie inside root 3 distance from the origin. So this one won't come in W, but this one will. So that together with the origin forms our W. And it's not a pretty side, it looks horrible.
Okay, so like how do we define the angles at which the V's hexagons are shifted by?
Very good question. So the angles are formally defined as, I was trying not to get into the calculative details, formally it's defined as nonsense. Yeah, for I is 0 to 5 and J varies from I think -2, -1 all the way up to 2, something like that.
Sir, what is this arc sine? It's like what is this angles?
Sine inverse.
No, sine inverse is fine. What are these angles of which thing?
So this is basically tabulating the angles of these edges with respect to the origin, or with respect to some fixed line, let's say this. And once you have the angles of the edges, you can figure out where the spindles go. So it's not fun. It's not fun. If you have a lot of free time to spare, maybe go through the calculations. But yeah. Any other questions?
Okay, so like when we constructed M, there must have been many overlapping vertices, right? Only then you could get
that is correct. That is true. That is true. So yeah, there will be several overlapping vertices. We sort of identify them. So W in fact has exactly 301 vertices. Someone did the calculations for me. I did not do this myself. And when you take 7 different copies of W and merge them together, this has exactly this many vertices M. So as you can see, this is not just 7 times W. Yes.
Do you know how did someone came with them? Because its definition is very weird.
Well, I can send you a link to the original paper that gives some enlightenment on how as to how someone would have come up with this sort of heuristics. Basically, the idea is to have a lot of spindle density, have tons of copies of the Moser spindle, and this vector something happens to work, and then you sort of arrange it in a hexagonal grid. But yeah, it's not easy.
So could you send that paper on Discord or?
Sure, I'll send the link on Discord later. Any more questions?
Okay, so like how much time did it take completely? Because like this proof was not like ununderstandable. So like at least it was like you could understand this for some proof.
How much
so like
time
how
did
much
it take
time
for
did it
what?
took for somebody
Take for what?
for like whoever did this to complete the proof?
I have no idea. Mathematicians typically do not mention in their papers how long it took. It would be a lot of embarrassing secrets if they did. So I have no idea, but yeah. Yes, I have no idea.
Oh, okay.
So just to give an idea of how bad the proof is, recall that M itself is not the final proof, final graph that gives our proof, right? Recall the steps here. Um, so we construct M, and then we took 52 copies of M, combined them, and so that H's form an L graph. So that final thing that has like exactly this many vertices. Yeah, so that's not a good thing by any standards. There have been attempts to like sort of simplify the final proof graph, and I think we have gone down to left 1500 vertex graphs. Still pretty bad. Yeah. Any more questions?
Okay, so like for the upper bound, like I mean, just on surface, it seems like very astonishing that there exists an upper bound, because like there
Yes,
exists like so many like
correct.
infinite
So
possibilities.
I'll actually go through the upper bound tomorrow and some related results. So we will see.
Oh, okay.
Yeah. Any other questions? Yeah. If Rohan, if you're there, I guess you can end the stream now.